Very good day. We are going to solve this problem. In this problem, a copper vessel at a temperature of 23 degrees Celsius. So this is the copper vessel, you can see. So in this copper vessel, the temperature is actually 23 degrees Celsius, right? And the weight of the copper vessel is 500 grams. So let's consider the copper vessel mass is 500 gram, or we could say this is half kgs. And indeed, we have to have the data of a specific heat for the copper, that is actually 390 joule per kg per Kelvin. Let's say this is C of Cu. And this copper vessel, we actually mix some water. So the amount of water, that is actually 200 milliliter. It means the mass of water is 200 milliliter, same as the gram. So we could write down, convert into kgs, that is actually 0.2 kgs. And the specific heat of water, this is well known. So to all among the students, we know that 4200 joule per kg per Kelvin. So these two values have to given in the question. So the temperature of the water, that is actually 75 degrees Celsius, that is also given in the question. What we have to calculate in the very first part of the question, that is compute the final temperature of heat exchange. So this water actually put here within the copper vessel. What happened? The copper vessel will be heat gain, and because this is actually 23 degrees Celsius and water is 75 degrees Celsius. Indeed, this water, when we mix this water into the copper vessel, this water actually heat will be loss, right? So what is the heat gain by the copper vessel when water is added? So we could write down, let's say the heat gain is equals to 𝑚CΔ𝑇. So of course, when we mixing this scenario, so there will be a mix temperature. So let's say the final temperature is TF. Indeed, the mass of copper is 0.5 and value of C of copper is 390. And here the temperature actually 23. So as it is gain, so 75, 23 and TF. Which one is the bigger one? Of course 75. This is the part of the heat lost. But for heat gain, here the relation between the temperature is 23 and the TF. Indeed, TF minus 23 degrees Celsius, right? Now heat loss, let's write down heat loss is equals to M of W, copper, and write down here copper. Now C of W and del theta, right? So here the value MW is equals to 0.2 CW4200, and the temperature difference is nothing but 75 minus T of F. So in this context, we have got the value of heat gain and heat loss. Now we have to use the formula of calorimetry. So by the formula of calorimetry, we know that heat gain is equals to heat loss, right? So let's plug in the value of heat gain, that is actually 0.5 times 390, and the value of TF, let's plug in the value. So this will be 195 of the final temperature. So multiply this 2 with this one, and again it will be 23. So we could write down 4485 equals to, here we actually multiply this term with 23, so we have 4485, as well as we multiply with this part with 75, that is 63000, and the multiplication with the final temperature with this part, that is actually 840 TF. So let's calculate 840 plus 195, so that is actually 1035 of TF is equals to 63000 plus 4485. So the final value of the mixture, so the final answer will be 65.2 degree Celsius. So this is the final answer actually for the first part of the question. So the first part was the compute the final temperature during the heat exchange between the copper vessel and the 75 degrees Celsius of water. And the second part of the question is determine the actual contraction of water. It is appear the contraction is 1.49. So let's solve the problem of the second. So for the second part, the important formula to solve the problem, that is actually the actual contraction is equal to the apparent contraction and the vessel expansion. Indeed, we have to know the vessel expansion, that is very important to determine. Indeed, the volume expansion coefficient or the volume coefficient of the copper, gamma, is equals to, we could write down 3 alpha, and the alpha of copper, this value also have to given in the question. Anyways, let's consider the copper linear expansion, or the alpha value of the copper is equals to 16.7 into 10 to the power minus 6 per Kelvin, right? So we know the vessel expansion, the volume gamma is equals to 3 alpha. So let's calculate the value with multiply with the 3. So we have the value of 50.1 into 10 to the power minus 6 per Kelvin. And here the drop of temperature, right? So the drop of temperature, which is very important. So the copper vessel, it was actually initially 23 degrees Celsius, and when water is pouring within the copper vessel, indeed the final temperature is actually 65.2 degrees Celsius, right? The mixture or the final temperature of the mixture from the first part, that is 65. Anyways, the drop of temperature of water, so it was 75 degrees Celsius of the water, and the heat lost and the mixer temperature, that was actually 65.2 degrees Celsius. So we have 9.8 degree Celsius. And initial volume of the water, that is actually V0, that is actually 200 milliliter from the question, right? And V actual is equals to gamma V0, the initial value of or initial volume of the water, and the temperature difference, right? Now let's plug in the value gamma, which is 50.1 into 10 to the power minus 6. Initial value of V0, that is actually 200 milliliter, and the change of temperature for water, that is actually 9.8. So this is actually milliliter, by the way. That is very important in the context of unit. So it is milliliter. So we have the total amount of the actual contraction of water, that is 0.098 milliliter, right? So what was the main formula? The actual contraction. So actual contraction means the apparent contraction, which is actually given in the question, that is 1.49 milliliter. That is actually given in the question. Remember, let's check the question. That was actually 1.49 milliliter. And here 1.49 plus the vessel expansion, that is actually 0.098 milliliter. If we sum up this two value, what we have? We have the value, the actual contraction is equals to 1.59 milliliter. The del of V actual. So this is the second part answer. Hope you understand. If there any question, any confusion, or anything you would like to know from my side, I would love to help you in physics, math, and ICT as well. Have a good day. This is the extensive question of the very first question. Here the copper vessel temperature was 23 degrees Celsius, and the final temperature is 65.2 degrees Celsius. Now in this question, the temperature is increased by 5 degrees Celsius. It means we have to add more 5 degrees Celsius. Now calculate the extra amount of water needed to maintain the equilibrium. It means here the previous, it means the very first question, mixing temperature or the final temperature, that was 65.2 degrees Celsius. Now more 5 degrees Celsius need to be added or need to be increased. So the temperature is now 72 degrees Celsius, the final temperature or the mixing temperature. Indeed, of course, before it was 200 milliliter of water. Now the extra amount of water need to be added to maintain the equilibrium position or situation, right? That has to be calculated. Indeed, the final temperature increased by 5 degrees Celsius. So for 5 degrees Celsius temperature increased, the temperature is of course 70.2 degree Celsius. Now the heat loss and the heat gain. So this is actually the final temperature, by the way, again. So this brush container or the vessel heat gain, let's say this is heat gain, is equals to mc of c and del of theta. So it was, the value is of course half kg, 390, and the temperature difference is now, of course, the final temperature is how much? 70.2 minus 23, right? Because it is 23. So how much we got? The value is 9092.3. Heat gain this amount, right? Now heat lost by the water, that is again m. And by the way, this time we have to use the new mass. So m of new times 4200, and the temperature difference, that is actually how much it was? It was 75 degrees Celsius of the water, and the mixing temperature, that is actually 70.2. So here the value will be 19757.92 of m nu, right? By using the calorimetric formula, so this is actually the heat gain, right? So we know by using the calorimetry formula or by the calorimetric principle, this will be principle, PLE, not PL. Anyways, so we could write down m nu is equals to, we could write down 9092.3 over 19757.92. So the new mass will be 0.4605 kg. So this is the new mass, right? So how much water need to be increased for the equilibrium position? So m, the previous one, it was how much? It was 0.2 kgs, right? So plus m of extra that we have to calculate right now, and the new value is how much? 4605. Of course, this is the fractional value, Anyways, so the extra amount of water is equals to, so this one minus this value, so 0.4605 minus 0.2, it will be 26.2605 kgs or 260.5 grams need to be added. This is the first part of the second question. Now the another part is 0.5 kgs of wire. This is the wire is absorbing about 950 joule of heat. As a result, the raising temperature is 30 Kelvin. Determine the wire specific heat. So we have to calculate in this question the value of C of wire is equals to what? This is need to be determined in this portion. In this context, or in this part, the mass of wire, let's say this is wire by the way, Wi is equals to 0.5 kgs from the question, and the heat absorbed, so let's say Q absorbed is equals to 1950 joule, and temperature change, so del T is equals to 30 Kelvin. So the heat capacity, or the specific heat capacity, the specific heat capacity Q is equals to mc del theta. So here the value for the specific heat of the wire is equals to Q over m of del theta, right? So what is the value of absorbed heat? That is actually 950, and the value of m, that is actually 0.5, and the change of temperature, that is actually 30 Kelvin. So we found 130 joule per kg per Kelvin, and this is the answer for the second part. In this problem, the vessel of the aluminium mass is 300 grams, and the temperature of the vessel before pouring the water, that is actually 25 degrees Celsius. Now the water, the hot water, the temperature of the water is 80 degrees Celsius, and the mass of the water is 200 grams. Now this water actually pouring within this container, the aluminium vessel or aluminium container. Now there will be a mixed temperature, or the final temperature. Let's say this is the final temperature, that is actually TF, that we have to calculate, and the aluminium specific heat, that is actually 900, and the specific heat of water, that is 4186. Literally we are using actually 4200, doesn't matter. In this time we are going to use actually 4186, whatever given in the question. Anyways, so we have to calculate the final temperature for this question, right? So within this interaction with this water and the aluminium container, there will be two incidents happen. By the container of the aluminium, heat is gained because the hot water of 80 degrees Celsius, when pouring within the container, the heat is gained by the aluminum container. So the equation will be m of c cc, specific heat of the by the way, this will be aluminum, beg your pardon, aluminum, and the temperature difference. So the mass of aluminum container, that is 300 grams, it means 0.3 kgs, and the specific heat of the aluminum is 900, and the temperature, it is 25 degrees Celsius, and the final is TF. So TF minus 25 degree Celsius, right? And the water, when mixing with this, I mean pouring within the aluminum container, in that sense the heat released or heat lost by the water, so heat lost MW CW and del of T, right? So the mass of water is 200 grams, it means 0.2. The specific heat given as 4186, let's plug in the value, and the temperature difference. So the temperature is 80 and TF, so 80 minus T of F, right? And we know the formula of calorimetry: heat gain is equals to heat lost or heat loss within a system. So in this system, heat gained by the aluminum container, that is actually by the aluminum container, that is 270 after multiplication with the value. So T of F minus 25 is equals to 0.2 times 4186 is 837.2, and 80 minus T of F, right? So we could write down 1107.2 of TF is equals to 73726, and TF is equals to 66.6 degrees Celsius. So this is the final answer for the question, right? In this problem, there is a brush block, mass of 0.6 kgs. Let's first write down. So mass of brush is equals to 0.6 kgs, and the specific heat of this brush we have to calculate. This is the final question of this question anyways. And the temperature of this block is 120 degrees Celsius. Now this block need to be thrown within this water, and the water mass is 0.4 kgs. Temperature is 30 degrees Celsius. It is actually a room temperature of the water. Anyways, when this block is thrown within this water, the mixing temperature is about 40 degrees Celsius. This is also given. What we have to calculate? We have to calculate the specific heat of the brush. So this block is actually heat lost. So heat lost by the brush block, that is M, C, and the del theta. What will be the value? The value is 0.6 kgs, the specific heat of the brush that we have to calculate, and the temperature difference, that is actually 120 minus the final temperature, that is actually 40 degrees Celsius. And the water, the heat gain actually, because when the brush block throw within the water, what will happen? The water actually heat gained from the brush block, and this is 𝑚CW and del of T. And we know that by the formula of calorimetry, the heat loss is equals to heat gain. So this value is equals to, so let's write down here, or is equals to the mass of the water, that is actually 0.4, and the specific heat of the water, that is 4200, and the temperature difference, that is actually the final temperature, which is 40, and the temperature of the water is 30 degrees Celsius. Now here we have to calculate the value of the specific heat of the brush block is equals to 349 joule per kg per Kelvin. So this is the final answer. In this example, 250 grams vessel made by copper vessel at 30 degrees Celsius hold 300 grams of water at 90 degrees Celsius after mixing. What does it mean? Initially, this copper vessel, the temperature is about 30 degrees Celsius and its mass is 250 grams, and the water on the other cup or other container, 90 degrees Celsius, hot water obviously, and amount is about 300 grams, that mixing together, let's say here. Now the mixing temperature, now let's say 70 degrees Celsius, specific heat of copper is 390 joule per kg per Kelvin. Verify the heat is lost or conserved, that we have to verify. Anyways, so mass of the copper is equals to 250 grams, or we could write down to 5 kgs, and of course the value of specific heat is 390 joule per kg per Kelvin. On the other hand, the water, mass of water is 0.30 kgs and the specific heat is 42 joule per kg per Kelvin. So here what is happening, the copper container actually heat gained, right? So heat gained equals to mc del of theta or del of t. Let's plug in the value here. 0.25 times 390 and the change of temperature, so it was actually 30 degrees Celsius and the mix temperature is 70, so of course 70 minus 30, altogether we have got the value about 3900 joule. And now water, so the water have got about 90 degree of Celsius temperature, so the mixing is 70, what does it mean? The water actually lost its heat. So in the context of water, it actually lost. So heat loss is equals to same mc of del theta or del T. So it will be for water and it will be water as well. So let's plug in the value of mass of water is 0.30. Cw specific heat is 4200 for water, because this is actually hot water or water, doesn't matter. Each of the case for the specific heat for water is 4200, and the temperature, final temperature is 70 and water is 90. So 90 minus 70, right? So what we have 25116 joule, right? So in this system, by the formula of calorimetry, that the heat loss is equals to heat gain, right? It has to be a common empirical formula for the system where actually heat is losing or heat is gain. Indeed, it should be heat gain equals to heat lost, right? But what we have here, the heat gain about 3900 and heat lost is 25116, which is not equal. So the question, what we have to verify, we have to verify whether heat is lost or conserved. So indeed, heat is lost or conserved, that we have to comment, right, within the answer of the question. As this is not equal, why this is not equal, that we have to give a strong comment for this question. So here, of course, here heat is more actually. Indeed, the heat is not conserved actually. As a result, the heat is lost by the water. So this comment is very important to understand, that heat lost by this amount of water, of course, it is significantly greater than the heat gain by the copper vessel, which is 3900 of joule. This is indicate that the large number of heat energy, it means 25116 minus 3900, which is 21216 joule, was lost by the surrounding of the environment. So this is actually the final comment for this problem. In this problem, actually two parts of this question. First part is 0.75 kgs of unknown metal. So this is actually a unknown metal, this one, this bar, and the mass of this bar is 0.75 kgs. It actually absorbed 3600 joule of heat. Initially it was actually 25 degrees Celsius from the question, of course, and after absorbing 3600 joule of heat, the temperature rises to 65 degrees Celsius. We have to identify what is the materials or the bar is made of, which material we have to identify. So the mass is 0.75 and Q, I mean the absorbed heat is 3600 joule. Initial temperature T1 was 25 degree Celsius, absorbing the heat of 3600. The temperature rise to 65 degrees Celsius. So the temperature difference 𝑚CΔ𝑇 65 minus 25, so it will be 40 degrees Celsius. So our main target to identify the metal, right? Indeed, we have to identify its specific heat. So if we know the specific heat of the metal, so we can define, okay, this is the name of the metal. So we know the heat is equals to 𝑚CΔ𝑇 or del T. So we have to determine the value of C, Q over 0.75 times 40. So the value of C is equals to 120 joule per kg per degree Celsius. So to find out the name of the materials defined by the specific heat from the table, of course in this question obviously there will be given a table where couple of material name and their specific heat as well. So let's say this is iron. So let's say this is iron and this is lead, and the value of C is, let's say, given 100 and this is 120. This type of table has to be attached with this question. So our final value is 120. Indeed, the material made by lead. So this is the answer for the very first part of this question. Now the second part, which is completely differ from the first portion. Anyways, how much ice at 0 degrees Celsius must be added 400 grams of water at 40 degrees Celsius. So in this container or this cup or vessel, here actually the temperature of water is 40 degrees Celsius. Now within this water vessel we have to add ice, and obviously the temperature of ice is 0 degrees Celsius. Now we have to add as much as ice we have to add it within this water, and this water will become obviously 0 degrees Celsius. The mixing temperature will be 0 degrees Celsius. This is our target. So what we have to calculate? We have to calculate the amount of ice. It means the mass of ice we have to calculate. And obviously the latent heat of fusion of ice is 3.36 into 10 to the power 5 joule per kg. Anyways, now let's solve the problem for the part B. So the mass of water is 0.4 kgs. Initial temperature T1 is equals to 40 degrees Celsius of the water, and initial temperature of ice is 0 degrees Celsius, and the final temperature of the mixture, that is actually 0 degrees Celsius as well, and the mass of ice we have to calculate. So here the glass of water, of course, and the amount of ice added here. So the temperature of ice is 0 degrees Celsius and amount is m kgs that we have to calculate, and the mass of water is 0.4 kgs and the specific heat of the water always 4200 joule per kg per Kelvin. Mixing temperature or the final temperature is 0 degrees Celsius. It means we have to make the iced water. So what we have to do, and there is actually the temperature of water is actually 40 degrees Celsius. Indeed, we have to add ice. So this water will become ice water and the temperature will be 0 degrees Celsius. So what is happening here in the context of ice, this ice will be melted. As a result, this ice actually heat is gained by the ice. So equation will be M and LF. So the mass of ice, it will be M that we have to calculate, and LF, latent heat of fusion of ice, is 3.36 into 10 to the power 5, right? And here for water, the heat is lost due to added of ice. So M, the mass of water, C of water, the specific heat, and the temperature difference. So the temperature of water is 40 degrees Celsius and the mixing temperature, that is also 0 degrees Celsius. So if we plug in the value of mass of water, that is actually 0.4, and value of C is 4200, and this is 40. So after calculation we have got 66976 joule, right? And by the definition of calorimetry, we know that Q lost is equals to Q gain, and this is for ice and this is for water, right? Anyways, so the value of heat lost, that is actually 66976, and here M times 3.36 into 10 to the power 5. So the mass of ice will be about 1993, or about 0.2 grams, pardon, it will be kgs actually, or we could write down 200 grams of ice need to be added to make the ice water. So this is the final answer for the second portion.